Thanks for introduction. Good afternoon. My name is Youngbo Aram Shim, and this study was done with my great collaborators, Jaeyeon and Geehyuk. We have explored through the concept of multimodal watchback tactile display using wind and vibration as a medium. Let me share you our work and some interesting findings today. Unlike other smart devices with large visual displays, we could not always occupy our visual attention to a smartwatch, as when you're riding a bicycle in this case. And tactile display is a viable supporting option to deliver on information, since the watch always contacts the skin of the user. So various tactile displays on the forearm have been introduced therefore. The most representative one will be vibration, which is already applied in commercial products. And other tactile stimuli includes wind, skin dragging, squeezing with SMA wire, light touch with brush, or simple tapping sensations. However, because of the small contact area of the watch, which is only about 40 millimeters in width, using a single tactile modality may have a limited information capacity. So to expand the information transfer, we considered using multiple tactile modalities on a same skin area. Using this multimodal tactile display, we could not only use each single modality such as vibration or wind separately, but could even combine various modalities and multiply the transmitted information. In this study, we have investigated the feasibility of multimodal tactile display on a watchback. We selected wind and vibration as a tactile modality pair specifically, since they have distinctive characteristics. For example, they stimulate different tactile channels. While wind mainly fires the hair follicle mechanoreceptor and thermoreceptor, vibration mainly stimulates fast-adapting receptor, the Pacinian corpuscle. Also, their intuitive feelings differ. Wind is subtle and soft, but vibration is highly arousing or even unpleasant sometimes. We thought the two tactile modalities complement each other well, and therefore the combination of these will be highly perceivable. We implemented a hardware prototype of a wind vibration multimodal watchback tactile display. To form a single tactor, we placed the micro fan first, and this side of the fan intakes the air, and this is the back side where the wind is emitted. We stacked sponge on the fan, then attached a linear resonant actuator on the top for vibration. The size of the LRA was smaller than the fan, therefore it did not block the airflow. This structure enabled us to give either wind and vibration stimuli on the same area of the skin. With a 3D printed housing and a strap, a 2x2 array type wearable device was completed. So now, we are able to deliver wind stimulation at different points. As you see, the fan is revolving on each point. Same for vibration. Two separate points are activated as shown with the animation. Independent control of each tactile modality means we could bring them in the same position and at the same time. The left upper part is activated at the same time in this video. Controlling these properties, some complicated patterns could be could be designed also, such as from vibration to wind. With the feasible hardware, we thought about how wind and vibration could be combined and what interaction scenarios could be made using wind and vibration tactile pair. In this section, we introduced some representative application scenarios and explain them in respect of the combination types of multiple tactile modalities, which is individual, simultaneous, and sequential. The first one, individual combination, used two tactile modalities independently. The stimuli made of wind is mapped to a specific application or service, while vibration stimuli is in charge with different application or service. The first example of this combination type would be touch state feedback scenario. Many hover tracking or pressure sensing touchscreen techniques have been introduced, and multimodal tactile display could strengthen this interaction. If the finger enters the hover detecting state, the wind is blown, and when the finger exerts pressure to the watch, or the right, pressure state's activation is known with vibration. However, we do not know yet if wind could be delivered in a complicated pattern to indicate the hover state. Therefore, our first research question was, can people discriminate a number of spatial-temporal patterns of wind as they recognize spatial-temporal patterns of vibration? The other research question relates to a specific case of individual combination. In this example scenario, wind feedback is assigned to a message notification, and vibration feedback is assigned to a metronome application. As you see in the animation, the metronome tick is delivered with vibration, and suddenly, the message notification breaks in. Because the two modalities are used totally independently, an overlap could occur for an individual combination. For this case, we suspected if people could recognize at least one of the tactile patterns by giving an attention to a specific one. That is, when individual patterns are overlapped, can people recognize one of the tactile patterns by giving an attention to a specific tactile modality? Different from overlapping individual cases, simultaneous combination exposes two tactile stimuli at the same time intentionally to form a meaningful signal. The next scenario suggests emphasizing the content of the smartwatch using multimodal tactile display. This case assumes the user is scrolling down a contact application on the smartwatch. So as you saw, wind is blown periodically for a short term to give a step feedback of scroll. And at the position of the favorite contact, wind and vibration combined in a timely manner to notice the user. It is an importance content. So we could say that simultaneous type combines the two modalities at the exact same time, but also could use independent spaces. If each tactile modality could employ multiple special points, there would be various special combination even for a single burst pattern. Yet, we do not know people could distinguish these multiple points. So we tried to find out, can people distinguish each position of vibration and wind stimulations when simultaneous pattern is provided? The last combination type, sequential combination, is a crossed exposure of multiple tactile modalities. This would be a good example of sequential combination. Let's say this is a single pattern to deliver somewhat kind of information. Throughout the interval of the pattern, the tactile modalities do not overlap but cross each other in a timeline. In other words, sequential exposure. Here is one sample scenario. Researchers have tried to convey alphanumeric patterns through a tactile display such as an etchfit by Liao et al. The left part of the figure indicates alphabet A in an etchfit pattern set, and pattern of number 7 is shown right. The study was done with single tactile modality only, the vibration. To deliver two patterns in series, a few seconds of interstimulus interval or a few seconds of vibration called delimiter is inevitable, because users won't parse the characters well without the delimiter. This solution requires additional time resource, however. But using a multimodal tactile display, the last point of each pattern could be exposed with a complement tactile stimuli, indicating the end of single character pattern and no additional time required. To make the case visible, we should know if people can discriminate the transition of tactile modality. 4 transition types exist as shown: vibration to vibration, vibration to wind, wind to vibration, and wind to wind. First question for the sequential usage is, can people discriminate the 4 types of transitions? In addition to the previous research question, we also investigated if people could discriminate spatial temporal sequential patterns. In an organized sentence, can people correctly discriminate sequential patterns that are combinations of transitions and spatial temporal patterns? So we came up with 5 research questions while verifying the possibility of various scenarios. For individual combination, first we want to know if wind patterns are distinguishable, And second, can we deal with overlapping patterns by giving an attention? For simultaneous type, we're curious about people distinguishing multiple points exposed at the same time. In sequential usage, we suspected that if people could discriminate tactile modality transitions, and second, the spatial temporal patterns. We conducted 4 experiments to answer the research questions, and for all experiments, random pattern recognition task was taken. The participants were exposed to a random multimodal tactile stimuli of about 1 second. We asked the participants to discriminate the random pattern given and recorded the answer. Based on the answers, we calculated the accuracy and the information transfer. Experiment 1 was designed to answer the first research question if people could discriminate wind patterns compared to vibration patterns. Simple 4 directional patterns, including right, down, left, and up, were used for each tactile modality conditions. This is the result of recognition. The vibration conditions accuracy and information transfer were significantly higher than those of wind condition as shown. In experiment 2, to see the effects of giving attention and overlapped individual pattern cases, we multiplied the pattern sets that we have used in the first experiment, which means we exposed 2 patterns from each set at the same time. Therefore, a total of 16 patterns were used. 2 test conditions were used. For the first one, we asked the participant to focus on the vibration pattern and discriminate the vibration pattern only. An opposite instruction was given for the wind condition. This is the comparing results of experiments 1 and 2. For both tactile modality conditions, the performance was significantly degraded in experiments 2. All recognition rate is higher than accuracy of answering by chance, which means it is possible to recognize specific tactile stimuli in overlapped cases, but it seems harder than perceiving a single modal pattern. Also, the results indicate that vibration dominates wind's sensation, which could be explained that the vibration just dominates the wind in this case. To answer if people could distinguish each position of vibration and wind, 16 simultaneous patterns were used for experiment 3. These were all possible spatial combinations of using 1 stimulation point for each modality. The accuracy of total pattern set was about 30%, quite low, but still higher than guessing by chance. And we particularly analyzed if the participants have at least discriminated the position of vibration regardless of wind position. The accuracy was about 65%, while for wind, the accuracy was about 44%, lower than vibration. It follows the previous results of experiment 2, vibration dominating the wind. Experiment 4 was designed to investigate if people could recognize transition types and spatial temporal patterns. So simple sequential patterns, which is combination of 4 transition types and 4 directional patterns were used. Directional patterns were same as experiments 1 and 2, right, down, left, and up. And each quadrant of the figure indicates the transition type. The total result showed an accuracy of about 78%. And as before, we particularly analyzed the result based on direction group and transition group. For direction group, the recognition rate was about 78%. And interestingly, when we calculated transition types accuracy, it revealed a higher performance of about 98%. This is an overall information transfer of each combination conditions. The individual vibration pattern sets, individual wind patterns, simultaneous patterns, and finally the sequential patterns. The highest 3.29 bits, though the results are not directly comparable between the experiments since the test conditions differed, we could say that the sequential usage looks promising. For example, delimiter scenario would be useful. One other interesting discussion point is the effect of single tactile modality to the multimodal usage. In our setting, vibration individual patterns were more perceivable than wind individual patterns. And this relationship was applied onto the sequential combination as well. As you see, each transition type's accuracy is in relation with ratio of its composing tactile modality. This implicates if each single tactile modality earns a high information capacity, the better the result of multimodal combination will be. It is really an advantage of multimodal tactile display, since previous studies on single tactile modality could be also useful for multimodal tactile display. As a conclusion in this study, we investigated the feasibility of wind vibration multimodal tactile display. We proposed a series of application scenarios for combining wind and vibration. And the results revealed that the sequential patterns are highly perceivable. There were some limitations, such as the prototype we have used had a short distance between tactors to fit the size of the wrists, and this might have degraded the performance. We have only tried wind and vibration pair this time, and as a future work, we will explore and try other tactile modality combinations with unique characteristics. So that is my talk. Thank you for your attention, and I'll be glad to take your questions.
Hi, Antoine Veil, McGill University, great talk. I have a question because you are like saying that mainly vibration is more perceived than wind, but you're using two different types of actuators. For example, I think the LRAs that you are using gives strong vibration, and you're using microphone that has a very small wind effect.
That's right.
So how do you level the difference? Like, for example, if you conduct the same study using strong wind, do you think that people will have different results?
Yeah, that's a really good question. And actually, that's right. I mean, the microphones had quite little magnitudes to stimulate the skin, and like the perceiving rate was actually low, and even in the individual cases. So if we use more stronger wind patterns, maybe we could achieve higher recognition rate, and also it could be maybe compatible with vibration.
Okay, thank you.
Thank you.
Thank you, and thank you for a great talk. I was wondering if you could expand a little bit on your finding about the sequential patterns going from vibration to vibration, because that's where you were finding the greatest accuracy and the lowest error by a country mile. Were you finding that it was just being able to tell the difference between, say, the vertical and the horizontal was what they were able to detect? Or did you also have findings about their ability to understand the difference between up, down, left, right? The directional part specifically in the vibration part of the study.
Can I re-elaborate your question?
Well, sure. Like when you're showing the charts before, you're showing accuracy was much higher when you're going vibration to vibration. That was your sequential analysis.
Yeah, that's right. So maybe you want to know the trend of directional patterns accuracy, right?
Correct. Thank you.
Yes, actually, the directional patterns had a trend, and like the up pattern was rather up patterns and down patterns were better recognized than left and right patterns, because there were some the participants were well recognizing it for like the vibration tactors were in the same columns. And this kind of findings were consistent from the previous works, and hope that could be an answer for you.
Thanks so much.
Thank you.
Hello, Paul, Texas A&M University. Can you go to the slide on the random pattern recognition?
Random pattern.
This was a question that we were curious about the design. So it was, I think, earlier in the presentation. It was titled Random Pattern Recognition. All right, so our lab had worked with different ways of trying to distinguish without having them seen the device, and we noticed that we had them covered with the sheet of with cloth, with walls, and I guess it was just initial findings. We noticed a slight difference. It looks like you used a cardboard box. Was it a convenience design, or was it something that was had some initial design justifications. I was curious about that.
So the use of box was primarily to block the visual attention of participants, since the microphone's rotating. We could see the participants were able to see it without the box.
Did the wind inside the box do anything special, or was it not noticeable by the users?
Because it blocks the airflow.
Because of the confined spaces.
Yeah. So actually, the airflow inside the microphone was not that strong. So I guess it didn't affect the users much. And yeah, that will be.
Thank you so much.
Thank you.
All right. Thank you for a great talk. I'm MJ from KAIST, and I just have one question out of curiosity. You mentioned 2 different channels for each vibration and the wind. I was wondering if it's possible to confuse the perception when you make a gradual change, so varying the degrees of one feedback and then moving to the other. Is it possible for them to be confused, or is there no chance of any confusion?
So you mean from vibration to wind, or wind to vibration?
Around, yeah.
Yeah, that's a really great question. We really want to. It's kind of. We didn't try it yet, and we are also curious about like continuous sensory changes from some kind of the tactile modality to other one, and yeah, we don't know yet, but yeah. That's a good research question, I think. Thank you.
Let's thank our speaker again, all of them.